College of Engineering and Technology. Now we are going to see about the dielectric properties of the materials. From the dielectric properties, here I am going to explain about the band theory of solids. The free electron theory explains the properties like thermal conductivity, electrical conductivity and the specific heat of most of the metals. But it fails to explain why some solids are conductors, some are insulators and others are semiconductors. A solution to this problem was given by band theory of solid and is called as bond theory. Postulates of the band theory of solids. According to the band theory, potential energy of the electron within the crystal is periodic due to the periodicity of the crystal. That is, free electron move inside the periodic lattice field. The potential energy of the solid varies periodically within the periodicity of space lattice alpha, which is nothing but the interatomic space. Alpha means interatomic of space. Next, Bloch's theorem for particle in a periodic potential. The motion of the electron inside the lattice is not free as expected, but the electron experiences a periodic potential variation. The potential energy on the electron is maximum between the adjacent ions and gradually decrease as the electron moves towards the ions as shown in the figure. From the figure we can see the potential energy of the electron is maximum between the adjacent ions and the gradual decrease as the electron moves towards the ions. Next, Bloch's theorem. It is mathematical statement gives regarding to the form of one electron wave function for a perfectly periodic potential. This statement represents if an electron in a linear lattice of a lattice constant A characterized by the potential function V of x, it is represented as V of x plus A satisfies the Schrödinger equation. The equation 1 represents the Schrödinger equations where the wave function, where chi of x is the wave function of the electron with energy E, and it is obtained as a solution of Schrödinger equations or of the formula chi of x equal to uk of x ei u suffix ikx, where uk of x represents uk x plus a. It is represented as equation 2. uk of x is a periodic with lattice periodicity. The potential of v of x is a periodic and it is represented as what? P of x equal to v of x plus a. A represents the lattice constant. From the Bloch theorem, we can say that the free electron is modulated by the periodic function uk of x eikx. In other words, the solutions are plane waves modulated by the function uk of x, which has the same periodicity as the lattice. This theorem is known as the Bloch theorem. The function of the type 2 is called Bloch. Function of type 2 means equation 2. It is known as the Bloch functions. Here we are going to see about the proof. From if equation 1 has a solution with the property of equation 2, we can write the property of the Bloch diagram, that is equation 3 as what? Psi of x plus a equal to e of I k x plus a uk x plus a, or we can also represent it in another form of this chi x plus a equal to e I k x e I k a uk x plus a. It is represented as equation 3. Here we can write and denote the equations as, we can denote as the following characteristics. uk x plus a equal to uk of x. We can write the above equation as what? Chi of x plus a equal to e I k x into e I k a dot of uk x. Same psi of x equal to e I k x uk x. We can write the above equation as psi of x plus a equal to e I k a psi of x. So final psi of x plus a equal to q, capital Q. It is we can substitute it as e I k a psi of x. If psi of x is a single valued function, then we can write psi of x equal to psi of x plus a. This the Bloch theorem is proved. Next, basic of chronic Penny model. The behavior of an electronic potential is studied by the considering a periodically rectangular well structure in one dimension. It was the first discussed by the Cronin and Penny in the year 1931. The potential energy of an electron when it moves in one dimensional perfect crystal lattice is assumed in the form of rectangular wells as shown in the figure. Here we can see the one-dimensional periodic potential of chronic Penny model. In the region where 0 xa, the potential energy is 0, and in the region of minus b greater than x greater than 0, the potential energy is v naught. The one-dimensional Schrödinger wave equation for the two regions are written as the above formula in the formula of the two regions where we defined below. Next, so finally the Schrödinger equation from the above substitution value d square sky by dx square plus beta square sky equal to 0, where beta square equal to 2, we can substitute the above value of 2m by h cross square v naught minus e. For the both the region, the appropriate solution suggested by the Bloch is of the form chi equal to ikx ukx. It is represented as equation 5, differentiating equation 5 and substituting in equation 2 and 4. Then the further p sin alpha a by divided by alpha a plus cos alpha a equal to cos of ka. So where alpha equal to root of 2me by h cross square, and the capital P represent m small m v naught b alpha by h cross square. The term P represent the scattering power of the potential barrier. It is measure of strength with which the potential barrier. It is a measure of strength with the electron are attracted by the positive ions. The equation is analyzed by drawing a plot between alpha, double alpha, and the P of sin alpha by alpha plus cos of alpha square. So here the plot represents the plot of alpha double alpha square by P sin alpha square by alpha square plus cos of alpha square. Next, from the graph we can conclude that the energy spectrum of the electron consists of a large number of allowed and the forbidden energy bands. The width of the allowed energy band, which means shaded portion, increases with the increase of energy values, that is increasing the value of alpha a. This is because the first term of the equation P sin alpha a divided by alpha a decreases within the increase of alpha a. In the limit P of alpha, the allowed energy band reduces to one single energy level corresponding to the discrete energy level of an isolated atom. That means A gives infinity. In the other extreme cases, when P gives 0, cos alpha A equal to cos Ka and alpha equal to K. So alpha square equal to K square. So 2 alpha, we have already seen alpha represent 2me by h cross square. So K represent the h square. So E equal to h cross K square by 2m. E equal to h square K square by 8 pi square m, which corresponds to the free electron model. This indicates that the particle is completely free and no energy level exists. Thus, by varying the P from 0 to infinity, we find that the completely free electron becomes completely bounded. Next we are going to see about the EK curve. The energy of the electron in a periodic lattice is given by the E equal to h square K square by 8 pi m dot h square. From the above equation, as h changes, the corresponding energy E also changes. For a free electron, the energy curve is continuous as shown by the dotted parabola. But for the electron in a periodic lattice, the energy curve is not continuous parabola and discontinuity occurs at the K equal to n pi by A. The zone between plus pi by A and minus pi by A is known as first Brillouin zones, and the second zone of has two parts from plus pi by A to plus 2 pi by A and minus pi by A to minus 2 pi by A. These zones are allowed energy band separated by the forbidden energy band and as it is shown in the figure. Next, classifications of insulators, semiconductors and conductors. We have already known. Conductor means it is defined as the substance which allows the passage of electric current through it is called as conductor. Examples: all metals, graphite, aqueous solutions of acid, and it has three types. The types of conductors were what? Electrical conductor, non-conductor, or insulator or semiconductor. So, what is mean by electrical conductor? Electrical conductor means substance which allow electric current to pass through them are known as the electric conductor. Example: acids and the base and salts. So non-conductor defined as what? The substance which do not allow electricity are called non-conductors. Example, rubber, wood, paper and all non-metals except carbon. Semiconductor means the substance which partially conduct electricity are called the semiconductors. The conducting properties of semiconducting properties are increased by addition of certain impurities called doping. Example, silicon, germanium. On addition of B group elements like we produce the N-type semiconductors. On addition of third group elements like aluminum produced P-type semiconductors. Next, we are going to see about the electronic conductors are of two types. One is metal conductor and electrolytic conductors. So, metallic conductor means conductance due to the migration of electrons. It is called conductor. Electrolytic conductors means conductance due to the migration of ions in a solutions of fused electrolyte is called electrolytic conditions. It has the metallic conductor is examples of metallic conductor means metals, graphite, and the examples of electrolytic conductor means acids and the bases. So metallic conductor also represent the passage of the current due to the electron flow. No chemical reaction take place. Here the passage of current due to the movement of ions, some chemical reaction takes place. Here then the metallic conductor has free electrons are responsible for electrical conductions. Here electrolytic conductors free ions are responsible for the electrical conduction. In metallic, mass is not transferred. In electrolytic, mass will transfer. In metallic, with increase of temperature, resistance increases and the conductance decreases. Here, with increase of temperature, resistance decreases and the conductance increases. Then next we are going to see about we have seen the conductor. Then we are going to see about the insulator. Insulator are the one type of materials or the substance which prevent the flow of current through them, because these types of material substance are substance that have free electron in their atomic structure. That's why the electrons are unable to move from atom to atom. In other words, we can say that the insulator is poor conductor as of electricity or heat. It has high resistivity that prevents the flow of current. These types of material do not allow to transfers of electron from particle to particle. And types of insulator. There are different types of insulator. Pin insulator, post insulator, suspension insulator, strain insulator, bushing, etc. So now we are going to see about the pin insulator. The insulator is mounted on a pin on the cross arm of the pole. These type of insulators are great for transmitting and distributing communications and electric power. It can work for voltage up to 33 kilovolt. So then post insulator. This is the this one is more compact and a great alternative to the pin type insulator. It can be used on the lines up to 69 kV and sometimes even 115 kV. Suspension, then next suspension insulator. These type of insulators are used for voltage that are higher than the 33 kilovolt. It is composed of many glasses or porcelain discs that connect via metals links in a string form. In voltages higher than the 33 kilovolt. Pin insulators are not an economical option because of the size and weight. Strain insulator next. This electrical insulator has been made to work under the mechanical strain. Thus, it can endure a suspended electric cables pulls. Mostly these type of insulators are used in overhead electrical wiring. They help in supporting radio antennas as well as the overhead power lines. Next, shackle insulator. Earlier, this insulator came into use of strain insulator, also called the spool insulator. Shackle insulator are now used for distribution lines with low voltage. They can be found in both horizontal or vertical position. Bushing, it is a hollow electrical insulator that permits the passing of an electrical conductor through a conducting barrier without classification, structural, chemical classification, and the process of manufacturing. Now we are going to see first of all thermal classification. Thermally, the insulators are classified into 7 types and the classes are class Y, class A, class E, class B, class F, class H and class C. Here class Y limits the temperature is 900 degree and the material comes under class Y are cotton, paper, silk and similar organic materials. Class A limits temperature about 1050 degrees Celsius and the materials come under the class A are integrated paper, silk, polyamide, cotton and resins. Class A limits the temperature is 1200 and the material comes under class E are enameled wire insulations on the base of powdered plastic, polyvinyl, epoxy, resin, etc. Then class B limitations temperature is 1300 and the material come under class B or inorganic material impregnated with varnish. Class F limited the temperature is 1550 degrees Celsius and the material come under the class by or mica, polyester, epoxide, varnished in the high heat resistance. Class H limits the temperature is 1800 degrees Celsius and the material come under the class H are composite materials on mica, glass, fiber, etc. Then class C. Finally, class C limits the temperature of greater than 1800 degrees Celsius and the material comes under the class C are glass, mica, quartz and ceramic, teflon, etc. Next, we are going to the physical classification of insulating material. Physical classifications of insulating material is classified into 3 types: solid, liquid, gases. The solid insulating materials are fiber, ceramic, mica, glass, rubber, and resins. The liquid insulating materials are mineral oils, synthetic oils, transformer oils, and resin oils. The gaseous insulating materials are air, hydrogen, nitrogen, and sulfur hexafluoride. Then chemical classification. Chemical classifications of insulating material is classified into 2 types. They are organic and inorganic. The process of manufacturing. The process of manufacturing is classified into 2 types. They are natural and synthetic. Some of the insulating materials are fiber classes: mineral wool, cellulose, and natural fiber, polyester, polycyanide, polyurethane, insulin, resin, phenolic foam, urea foam, etc. Then next we are going to see about the semiconductors. Semiconductor materials are very important from the technology point of view. Devices made from the semiconductor materials now form a necessary part for all instrument and gadget used in the science, technology and engineering. These devices are in the form of diodes, transistors and integrated circuits. On the basic of electrical conductivity or electrical resistance have been broadly classified into 3 categories: metals, semiconductors and insulators. So metals have the electrical resistivity as low as 10 to the power minus 6 omega cm. Insulators have the resistivity as high as 10 to the power of 20. So semiconductors have the resistivity in between these 2 extremes. But the specialty about the resistivity of the semiconductor is that it is very much temperature dependent at absolute zero and it behaves as a perfect insulator, and at high temperature it can compete with metals. Then we are going to see about the band gaps of the semiconductor material. The magnitude of the band gap ID differentiate between an insulator and a semiconductors and decide many other properties of semiconductor. Generally, materials with the band gap less than 3 electron volt are considered a semiconductor under the practical condition. These are the list of materials and symbols and its band gap value. Here we can see the materials of silicon. Its symbol we have already known. Silicon is a band gap is 1.11. Germanium Ge, we know the band gap 0.61. The gallium arsenide Ga capital A as 1.43 and gallium antimonide GaAb 0.7 and gallium phosphide GaP 1.35. Then indium arsenide InAl 0.36, indium phosphide InP 1.35, aluminum antimonide accuracy 1.73. Next we are going to see about the types of classifications of semiconductors of pure and impure type. First the category comprises the pure semiconductor. It is called intrinsic semiconductor. In this semiconductor, most of the properties of the structure depends on the absolute zero. The intrinsic semiconductor behaves as an insulator and their conductivity increases with increase in temperature. But this semiconductor remains poor conductor of electricity at temperature of interest. The most common examples of the intrinsic semiconductor are silicon and germanium, which passes the energy band gap of order 1.1 and 0.70 electron volt respectively. The second category constitutes the semiconductor with impurities, which are called as extrinsic semiconductor. The electrical conductivity of silicon and the germanium include many fold with the addition of very small as impurities. Common examples of the extrinsic semiconductors are SiAs, silicon arsenate, silicon indium, germanium arsenate, and germanium indium, in which the first element represents the host semiconductor and the second element represents the impurities. The properties of the semiconductor changes drastically within the presence of even very small element of impurities and other impurities. Next, intrinsic semiconductors. Here we are going to see about the intrinsic and extrinsic. First we are going to see about the intrinsic semiconductor. Intrinsic semiconductor. Silicon is considered as a representative material of intrinsic semiconductor with the atomic number of silicon is 14 and the valence is 4. It has a crystal structure like that of diamond with a tetrahedral bonding between the atom. Every silicon atom is bonded to 4 other silicon atoms. Each bond is a covalent in which one electron is contributed by the central atom A and the one form the other bonding atom. At the absolute zero, the condition will remain intact. However, as the temperature rises, a silicon atom may get ionized, which means that it will lose one of its electron that may move freely in a crystals or may move with very less interaction with atom, which may come in its path. Among the very large number of atoms in the crystal, there is only one silicon atom that is short of one electron, and among the very large number of electrons in the crystal, there is only one electron which is free to move in crystal. In the language of the band energy of solids, 4 electrons from each silicon atoms in the crystal together from the valence band, and the electron that is free to move inside the crystal is supposed to lie in the conduction band. Next, the deficiency of one electron in the valence band is hole. The situation at this instant is that there is a hole in the valence band and an electron in the conduction band, and this condition has been reached because of thermal energy. In the above situation, the electron is at a high energy compared to that of the hole, which is a space devoid of the electron that has been promoted to the conduction band, and the electron that has been promoted to the conduction band will like to occupy its previous positions of lower energy or the hole in the valence band. When the conduction band electron falls to the positions of the holes and gets settled, the extra energy it has as a free electron is radiated out in the form of electromagnetic wave. And this process of excitation of electron to the conduction band under the influence of the ambient temperature energy and then getting back to the void, it is known as radioactive recombination. In actual crystal, there is not just one electron but quite large number of electrons depending on the temperature. The process of excitation of the electron and the recombination with the holes will continuously occur, but statistically at any temperature T not equal to 0 Kelvin, there will be a lot of electron in the conduction band and equal number of holes in the valence band. The number of electron in the conduction band is exactly equal to the number of holes in the valence band. At absolute 0, T equal to 0 Kelvin, the valence band is completely full while the conduction band is completely empty, and both are separated by a energy band gap of 1.1 electron volt. Next, electron volt can cross a gap of 1.1. The answer is what means the thermal energy is very small compared with the band gap. So that the room temperature and intrinsic silicon semiconductor behaves nearly as an insulator. The answer lies in the statistical distributions of the energy of a particle in an example of the particle maintained at a particular temperature. Electron gas means what? Free electron of the semiconductor. It is maintained at 300 Kelvin as a maximum distribution of energy. So here some electrons have an energy tending towards 0 and some tending towards the infinity. In this example, many electrons will have energies greater than 1.1 electron. These electrons will jump from the valence band to the conduction band. After some electrons have reached the conduction band, there will be a redistribution of energy of the remaining electron according to the Maxwellian statistics. Some electrons will again gain energy more than 1.1 electron and will go to the conduction band. This process occurs repeatedly and simultaneously. The process of electron holes recombinations will also occur. Finally, an equilibrium distributions will be achieved in which there will be n of x electron in the conduction band at 300 Kelvin. There are two categories of insulating semiconductor: the direct band gap and indirect band gap. What is meant by band gap? The minimum energy difference between the top of the valence band and the bottom of the conduction band. So the bands are represented what? E means energy and K versus K means wave number curves in brilliant zones. So direct band gap semiconductor means if the K value corresponds to the minimum energy state in the conduction band and the K value corresponding to the maximum energy state in the valence band are the same. The band gap is said to be direct, or we can say it in the other one means what? The direct band gap semiconductor is the one in which the maximum energy level of the valence band aligns with the minimum energy level of the conduction band with respect to the moment. In the direct band gap semiconductor, the direct recombination takes place with the release of the energy equal to the energy difference between the recombination particles. Then indirect band gap. Here, if the K value corresponding to the minimum energy state in the conduction band and the K value corresponds to the maximum energy state in the valence band are not the same. The band is said to be indirect, or it can be represented as an indirect band gap semiconductor is one in which the maximum energy level of the valence band are misaligned within the minimum energy level of the conduction band with respect to the moment. The electron which is lifted to the conduction band from the valence band has to interact not only with the optical photon but also with a lattice vibrations which is slowly processed. In the classes of semiconductors, an electron can jump from the valence band to the conduction band in two ways. First path, an electron can flow the path PQR. Here we have seen in the diagram PQR, in which both the momentum and the energy of the electron changes. The moment of the energy in the valence band increases by h cross k dash, it going from P to Q, and then it gains from going from Q to R. The second path, an electron in the valence band can be promoted directly upward to the higher energy state at the same moment along the path PS. Then the excited electron falls down into the conduction band minimum along the path SR by gaining the moment but losing the energy. Next, extrinsic semiconductor. The pure or the intrinsic semiconductors are generally made from silicon atomic number 14 and the germanium atomic number 32. They have the valence band and the conduction band of about 1.1 electron volt and 0.666. They are doped within the some impurities to make them more useful. These impure semiconductors are extrinsic semiconductor. The deliberate additions of carefully chosen impurities to silicon, germanium and other doping and other something called doping. The impurities added are in very small quantities of the order of few part in a million part of the host. Here, the silicon and the germanium belong to the fourth group of the periodic table, and impurities added are far from the third of the silicon atom with 4 valence electron per atom. The group state, the ground state energy of the third group element is higher than the upper edge of the valence band of silicon and germanium. The ground state of the energy of the fifth group element is lower than the lower edge of the conduction band of silicon and germanium. Amounts of impurities and the electrical conductivity of the semiconductor. The additions of small amount of impurities increases the electrical conductivity of semiconductor. What and all means EM semiconductor. Consider a silicon crystal with the pentavalent substitution impurities that is making silicon arsenate semiconductors. Four electrons of arsenate impurities participate in the formations of covalent bond with the neighboring silicon atom, while the fifth electron does not participate in the covalent bond and is loosely bonded on the atom. As a result of weak binding, this electron moves away from the impurities, making it positively charged ions, that is As+1. The force attractions of the electrons and the impurities of ion As+1 makes the electron orbit around the As plus ion. The distance of the fifth electrons from the As plus impurities is such that its ground state energy is below but very close to the conduction band of Si. Such impurities band is called as the donor band, and the electron is in it is also called donor electron. The energy difference between the bottom of the conduction band and the donor band is delta E electron, which is smaller than the thermal energy at the room temperature. On the other hand, the energy difference between the donor band and the top of the valence band is on the order of 1.09 electron volt, which is quite large. Therefore, at room temperature, the electron in the donor band jump to the conduction band, emitting appreciably electron conductivity. Such a semiconductor is an n-type semiconductor in which the number of electrons in the conduction band is greater than the number of holes in the valence band. That is n of E greater than n of H. So, therefore, the electron constitution the majority charges carrier and the holes the minority charges carrier in n-type semiconductors. Then p-type semiconductors. Trivalent impurities such as barium, aluminum, indium and gallium can be also substituted in the semiconductor. Here, the 3 valence electron in the indium atom form 3 covalent bond with this silicon atom, while the fourth bond contains 1 electron and 1 hole forming the unsaturated bond. The hole moves away from the impurity in indium impurities when neighboring electrons occupies its position. In this process, the fourth bond also becomes saturated and in impurities acquires negative charge, that is In-1, thereby attracting the holes towards it. The force attraction between the holes and the indium In-1 impurities ion makes the hole moves around in an orbit. The distance of the holes from the ion is such that its energy band lies above but very near the valence band. At the room temperature, the electrons from the top of the valence band jump to fill the empty states of the impurities band, thereby creates a holes in the valence band. The impurities band therefore is called as acceptor band, and the such semiconductor is called p-type semiconductor. The number of holes in the valence band is greater than the number of electrons in the conduction band, that is Ne of H. And therefore, finally, the holes constitute the majority carrier and the electron the minority carrier in a p-type semiconductor. Both the electrons in the conduction band and the holes in the valence band contribute towards the conduction properties such as the electrical conductivity of the external semiconductor. Hence, the external semiconductors are the material with mixed bonding, particularly ion and partially covalent. Donor impurities such as what? PSB and AS are used in the looping because of the donor bands formed with these impurities are close to the conduction band and therefore yield a significant carrier concentration at room temperature. Similarly, it is used as an acceptor impurities at the acceptor band formed by these impurities is close to the valence band. It is noteworthy that the transition metals such as iron, nickel, cobalt, copper is added with the silicon and germanium forming impurities bands far removed from the edges of the valence band and the conduction bands and therefore are not suitable for